Okay, everything looks like it's working okay. All right, so today we're going to get started on section 7.3. That's the integration of trig functions using substitution. Okay, so we know that the integral for du divided by the square root of a squared minus u squared is equal to sine inverse of u divided by a plus c. And the integral of du divided by a squared plus u squared. Oh, move that mouse off there. That's equal to 1 over a times tangent inverse of u divided by a plus c. And the integral of du divided by the absolute value of u times the square root of u squared minus a squared, that's equal to 1 over a times secant inverse of u over a plus c. Where we know that a does not equal 0. Okay. So if you take the negative of the sine integral, or the sine inverse integral, so if you say the negative integral of du divided by the square root of a squared minus u squared, that's equal to your cosine inverse of u over a plus c. Or you could just say we have a negative integral of du over the square root of a squared minus u squared. You can just say negative sine inverse of u over a plus c. These two are the same thing. But I believe that Newton only deals with the sine, tangent, and secant. I don't think they deal with the cotangent functions. Again, they could have changed it, but as of a month ago, they didn't. So, like I said, they upgraded all the time. So it's possible that they will accept this answer. But if not, you can just write it as a negative sign. Okay. Now, some of you probably went over this, and I think it was section 5.7, so it should look somewhat familiar, but we're still going to expand on it. These are the ones where it kind of fits into these forms, and we're going to look at the ones that don't quite fit into these formulas. Okay, so let's do one quick example, then we'll move on to the ones that don't quite fit. Okay, so let's say, for example, if we wanted to evaluate the integral, say the integral of dx divided by the square root of 1 minus x squared. Okay, so if you notice this one, it's really similar to the integral of du divided by the square root of a squared minus u squared, which is equal to sine inverse of u over a plus c. So it's just similar to, just as far as the form. So we can take our integral and rewrite it to match this form. So the integral of dx divided by the square root of a squared. So that 1, we can rewrite that as 1 squared. So if we had 25 there, we rewrote that as 5 squared. So we want to rewrite that as some value squared minus our x squared. And you don't have to use the parentheses. I just like to do that. I'll do the same thing with the 1. So 1 squared, where's my eraser? Here we go. I'm going to need that. Okay, so if we match up with the formula, we see here that a is equal to 1 and u is equal to x. And from that x, or that u, we can find our du. Okay, so our derivative of u is equal to 1 dx, or you could just say dx. Okay, so now we match everything up. That du is equal to dx, so we can replace that dx with du. That's equal to the square root of a squared, which is your 1 squared. And this is just the way I do it. You can do it whichever method you like. I always just go back and make sure all of them match up. And our u is equal to x, so that's just minus u squared. So if everything matches up, your dx, your a, and your u, we know that's just equal to sine inverse of u divided by a plus c. And then right here, all I do is replace the u and the a. So that's sine inverse of x divided by 1 plus c, which is sine inverse of x. All right, any questions on that one? Yes.
So like we gotta memorize all those like formulas, right? So we can recognize what's similar to one of them.
Yes.
Okay.
Yep. Just the 3 from the first page. That's why remembering those three is easier than remembering all six. So you're welcome. Okay. All right, anyone still writing? Okay. So let's say, for example, let me find a good one. That's a good one. Let's say if we wanted to evaluate the integral of 1 over 9 plus 4x squared with respect to x. Okay. So if you look at this one, if you notice, it's really similar to the integral of du, if we just moved our dx up here, divided by a squared plus u squared. And we know that is equal to 1 over a times tangent inverse of u divided by a plus c. So we want to rewrite our integral to where it kind of looks like the formula that it's similar to. So again, that dx, just move that up there. Or you can just say 1 over a squared plus u squared and put the du on the side. I just always put it up top. So that dx, I just go ahead and move it up there, divided by a squared. So we have a 9 there, but we can rewrite that as 3 squared. So it'll match here. So instead of 9, we'll put 3 squared. Plus u squared. So we have 4x squared, but we can rewrite that as 2x and that whole thing squared. So if we match these up, we see that a is equal to 3 and our u is equal to 2x. So as soon as we identify the u, that means we can find du. So the derivative of u is equal to 2 dx. So if we divide both sides by 2, you know that du divided by 2 is equal to dx. Bring it over. Okay, so now we just plug everything in. That dx, we can replace that with du over 2. Oops. The integral of du divided by 2. Or we can say 1/2 times du, same thing. Divided by 3 squared. So we can say a squared, because we did find our value for a. Plus 2x squared. 2x times 2x is 4x squared, so we did find that. So that du over 2, we can get that 1/2 and just factor it out to the front. So that's 1/2 times the integral of du divided by a squared plus u squared. Uh-oh. Okay, so we know that that's equal to 1/2 times, and that integral is 1 over a times tangent inverse of u divided by a. Well, we don't need the plus c on the inside of there. We can put the plus c on the outside. Plus c. So here, we just go ahead and replace our u and a. So we have 1/2 times 1 over a. A is equal to 3, so that becomes 1/3. Times tangent inverse of u divided by a, so that's 2x divided by 3. Plus c. Okay. So we do any simplifying if it's necessary, so we can go ahead and multiply those two. So you get 1 over 6 times tangent inverse. And 2x divided by 3, if you want, you can make it 2/3 x. Doesn't really matter which form you put it in. Plus c. All right. Any questions on that one? Okay, so we'll do one more using these formulas, then we'll look at the ones that do not look like those. Okay, so what if we wanted to evaluate the integral of 8 divided by the absolute value of 9t, and sometimes they'll put the absolute value, sometimes they won't, times the square root of 81t squared minus 64 with respect to t. Okay. So if you notice, this is really similar to the integral of du divided by the absolute value of u times the square root of u squared minus a squared. And that's equal to 1 over a times secant inverse of u divided by a plus c. So if they put t is greater than 0, then you know that you don't need the absolute value. So sometimes they'll put it, sometimes they won't. Okay. So first, we're just going to rewrite it to where it kind of matches this one. So that 8, I'm just going to go ahead and factor that out to the front, and that dt, just going to move that up there. So 8 times the integral of dt divided by the absolute value of 9t times the square root of 81t squared. We can rewrite that as 9t squared. Minus 64, we can rewrite that as minus 8 squared. Okay. So these two u's have to be the same because these two are the same. So we know that u is equal to 9t. So if you had just a t out here instead of a 9t, you just multiply this by 9 over 9, and it would have solved that one. So sometimes they may throw that at you. So instead of absolute value of 9t, they may have the absolute value of t. Okay, so we can see here that a is equal to 8. Okay, so again, as soon as you identify your u, you can find your du. So du is equal to 9 dt. So if we divide both sides by 9, we have du divided by 9 is equal to dt. Okay. So that gives us 8 times, we have dt, which is equal to du divided by 9. So you can say du divided by 9, you can say 1 over 9 times du, same thing. So it doesn't matter which one. Divided by, you have your absolute value of 9t, which is your u, times the square root of 9t squared. So we know that's u squared minus a squared. And that 1/9, we're going to go ahead and factor that out to the front. So 8 times 1/9 is 8 over 9. Times the integral of du divided by the absolute value of u times the square root of u squared. And make that squared a little bit neater. Minus a squared. Okay. So we know that will give us 8 divided by 9 times this integral, which is 1 over a, times secant inverse of u divided by a plus c. And once you get it right there, you're just going to replace your u and your a. So that gives us 8 over 9 times 1 over a. We know that a is equal to 8. So that's 1 over 8 times secant inverse of u divided by a. So that's 9t divided by 8. Plus c. So if we go ahead and multiply these two together, the 8's cancel each other out, so we're left with 1 over 9 times secant inverse of 9t over 8 plus c. All right, any questions on that one? All right. So let's say if you had one that did not fit any of those forms. Okay. What if you have an integral involving the square root of a squared minus u squared? Oops. Okay. So it involves it, but it doesn't have it in the form that we're looking for. So let's say, for example, just using that as kind of a template, what if you have the integral of dx divided by x squared times the square root of 9 minus x squared? Okay. Well, the square root portion of it is similar, but it has an x squared here, which is similar to this one, but this is u squared minus a squared, and this one will be a squared minus u squared. So it doesn't really match any of those. Okay, so if you have a problem like this one, you have the right angle where you have your u, your a, and if you use the Pythagorean theorem, this side is a squared minus u squared. So we know this is your angle, sine is equal to the opposite over the hypotenuse. So we know in this case, sine of theta is equal to u over a. So if we multiply both sides by a, we have u is equal to a times sine of theta. We know that cosine is adjacent over hypotenuse, so the adjacent is the square root of a squared minus u squared divided by a. So if we multiply both sides by a again, we get the square root of a squared minus u squared is equal to a times cosine of theta. As from the domain, well, for the domain, negative pi over 2 to pi over 2. Okay, and we'll solve this one after we go over the formulas. So what if we have integrals involving the square root of a squared plus u squared? Oops, straighten it up a little bit. Okay, so again, we have an a squared plus u squared, but there is no square root for the tangent inverse. The one we do have a square root for, that's u squared minus a squared. Let me straighten that up a little bit. So again, it doesn't quite match any of those three. A squared plus u squared, and that square root, we're going to use the right triangle, where this is our theta. So we have a and u, and we use the Pythagorean theorem, that's the square root of a squared plus u squared. Okay, so we know that tangent is opposite over adjacent. So tangent of theta is equal to u over a. So if we multiply both sides by a, we have u is equal to a times tangent of theta. And in the example, I'll show you how all of these fit in. We know that secant of theta is just a reciprocal of cosine. So that's the hypotenuse over the adjacent. So that's the square root of a squared plus u squared divided by a. So if we multiply both sides by a, that's the square root of a squared plus u squared is equal to a times secant of theta. And if we have, make sure, yep. We have integrals involving the square root of u squared minus a squared. Okay, so again, we have a square root of u squared minus a squared, but it's also attached to that absolute value of u. So that won't always fit. Okay, so we have our right triangle. We have our a and our u. If we use the Pythagorean theorem, that's the square root of u squared minus a squared. Okay. And again, we know that tangent is equal to opposite over adjacent. So tangent of theta is equal to the square root of u squared minus a squared divided by a. Or if we multiply both sides by a, we have the square root of u squared minus a squared is equal to a times tangent of theta. So we multiply both sides by a like we did here. If you have your square root, actually that's going to equal plus or minus a times tangent of theta is equal to the square root of u squared minus a squared. Okay. And the only reason that is the case is because you have from 0 to pi over 2 if u is greater than a. Oops. Make sure that a doesn't look like a 9, because that will give us positive value. But from pi over 2 to pi, if u is less than negative a. Which will give us a negative value. Whoops. And normally I would do like at least one proof, but these proofs are really, really long. I want to burn up 15 minutes of class time. Excuse me. All right, anyone still writing? No, right? Okay, so let's say if we wanted to evaluate the integral of dx divided by x squared times the square root of 9 minus x squared. Okay, so the first thing I would always try is to see if it fit one of the first three formulas. And we can see that it does not fit. And the closest one to it, excuse me, is the integral of du divided by the absolute value of u times the square root of u squared minus a squared, which is equal to 1 over a times secant inverse of u over a plus c. Okay. And it doesn't fit because we can see under the square root that u is equal to x. So this would have to be x for it to fit that formula. So if it weren't for that pesky x squared out there, we could just plug it right on in. Okay, so the first thing I would notice after realizing I couldn't use any of those formulas is that square root of 9 minus x squared. Okay, it's in the form of the square root of a squared minus u squared. So if we rewrite it, that's the square root of 3 squared minus x squared. You can use the parentheses, you don't have to, but minus x squared. So we can see here that our a is equal to 3. And our u is equal to x. Okay, so even though it doesn't fit one of our first 3 formulas, we still see that it can be solved. Okay, so we know that if u is equal to x and sine of theta is equal to u over a, then that means sine of theta is equal to x over a, or you can say x over 3. Let's go ahead and replace the 3 in that one step. So if we multiply both sides by 3, we see that x is equal to 3 times sine of theta. I was about to put sine of theta times 3 for some odd reason. Okay. So both of those actually have a place in our solution. So if you don't remember which triangle is which, all you have to do is that once you find your sine of theta, which in this case is x divided by 3, that's the opposite over the hypotenuse. You can kind of create the triangle yourself. So like I say, even if you don't remember it, you can still kind of create it on your own. And let me put a little rectangle around that. So if we recreate our right triangle, and this is our theta, the opposite is x, and the hypotenuse is 3. And if you use the Pythagorean theorem to solve for the missing side, you'd get the square root of 9 minus x squared. Okay. Now the goal of this, after doing these steps here, is that we want to replace our x squared and our dx. So the first thing we have to do is we have to find x squared, and dx. Okay. Well, luckily for us, we already found x. X is equal to 3 times sine of theta. Okay, so we have that. Now x squared is just 3 times sine of theta squared. So that means x squared is equal to 9 times sine squared of theta. So we found that one. And your dx, well, we just take the derivative of x. So we have our dx is equal to the derivative of 3 times sine of theta, which is 3 times cosine of theta with respect to theta. Oops, wrong. Okay. So it's all kind of falling into place. We've used this, we've used this. Now we have to find our cosine of theta. So everything here kind of has its place. Okay. So cosine of theta, which is adjacent over hypotenuse, is the square root of 9 minus x squared divided by 3. And again, you can put a little adjacent over hypotenuse as a side note. So if we multiply both sides by 3, you have the square root of 9 minus x squared. Make that squared a little clearer. 9 minus x squared. Square root of 9 minus x squared is equal to 3 times cosine of theta. And we'll finish it up on the next page. All right, anyone still writing? Right. Okay. So just writing down where we left off, we have x is equal to 3 times sine of theta. X squared is equal to 9 sine squared of theta. Dx is equal to 3 times cosine of theta with respect to theta. And we know that the square root of 9 minus x squared is equal to 3 times cosine of theta. So this may look like a bunch of useless information, but it actually falls into place. Okay, so if we take the integral of dx divided by x squared times the square root of 9 minus x squared, we replace those one at a time. So that's the integral, that dx, well, that's 3 times cosine of theta d theta. With respect to theta, instead of just saying d theta. Divided by x squared, which is 9 times sine squared of theta. Times the square root of 9 minus x squared, but we know that's 3 times cosine of theta. Okay. And if you're lucky, things will start to cancel out. Like this 3 cancels out with this 3. This cosine of theta cancels out with this cosine of theta. So that 9 in the denominator, we can go ahead and factor that out as 1/9 times the integral of 1 over sine squared of theta with respect to theta. Well, 1 divided by sine squared is cosecant squared, so we can just replace that with 1 over 9 times the integral of cosecant squared with respect to theta. So to find the integral of cosecant squared, we know that the derivative with respect to theta of cotangent is equal to negative cosecant squared. So if we integrate both sides, the integral and derivative are inverses of each other, so they cancel each other out. So we know that cotangent of theta is equal to the negative integral of cosecant squared of theta with respect to theta, but I'm running out of room. So if we multiply or divide, whichever one works, both sides by -1, we see that the integral of cosecant squared of theta with respect to theta is equal to negative cotangent of theta plus c. Oops. Okay, so since it's a negative cotangent, that's 1 over 9 times negative cotangent. I didn't want to skip that step of theta plus c, where if we multiply that -1 and 1/9, that's negative 1/9 cotangent of theta plus c. Okay, which is true, but we want our answer in the form of x, or in terms of x. We don't want them in terms of theta. So what we can do is we can go back, and I'm just going to copy our original right triangle. So I'm just going to copy it so I don't have to keep bouncing back and forth. So we have 3, our theta, our x, and this side, the square root of 9 minus x squared. Okay. So notice, not even notice, more remember. I don't think notice is the right word to use. I think it's more remember. We know that cotangent of theta is equal to adjacent over opposite, because it's the reciprocal of tangent. So we just apply this to that triangle. So that means cotangent of theta is equal to the adjacent, which is the square root of 9 minus x squared, divided by the opposite, which is x. I'll kind of put that in its own little box. So that means we go from this to equal negative 1/9. And we can replace cotangent of theta with the square root of 9 minus x squared divided by x plus c. Or we can simplify it a little bit more and just make it negative square root of 9 minus x squared divided by 9x plus c. I know it's a little bit tricky. All in all, for each one of these, like I said, depending on which form it's in, so if you had the square root of a squared plus u squared, you'd solve for tangent, u, secant, and your whatever a times secant is. Have all four of those ready and your triangle, and then you can just kind of replace it as you go. It says it takes a little bit of practice to get used to. It is tricky. So, all right, any questions on that one? All right. Okay, so let's say oh, anyone still writing? All right. Okay, so let's say, for example, if we wanted to evaluate the integral of the square root of 729 minus 81x squared with respect to x. Okay, so we can see here we can't use u substitution, because if we made u equal to 729 minus 81x squared, then that would just leave an x dx, but we don't have an x outside of that root function, so we can't use that. Okay, but luckily it is in the a squared minus u, well, square root of a squared minus u squared form. Okay, so if you remember, the square root of a squared minus u squared triangle. Okay, so you want to make sure you get your triangle. And that's where sine of theta is equal to u divided by a. And if we multiply both sides by a, u is equal to a times sine of theta. Okay, and these are just kind of notes, so it's not involved in actually solving, it's just what you'll need to solve it. So that right triangle, UA is your theta as the square root of a squared minus u squared. So we won't have to keep flipping back and forth to the other page. So we do the same thing we did before, is we take our square root, 729 minus 81 x squared. And we want to put it in the form of a squared minus u squared. So after a little trial and error, because it's not really a root function I know off the top of my head, square root of 729 is 27. So we can rewrite this as 27 squared minus 81x squared. So that just makes that 9x squared. So we know that a is equal to 27 and u is equal to 9x. Okay, so we have to find our u. So we know that u is equal to a times sine of theta. Well, u is equal to 9x. That means that 9x is equal to a, which is 27, times sine of theta. So if we divide both sides by 9, that gives us x is equal to 27 divided by 9 is 3. 3 times sine of theta. Okay, and our dx is equal to 3 times cosine of theta with respect to theta. Okay, so if we look at this as our integral of the square root of 729, we'll write it as 27 squared just to make it easier. Use an actual good eraser. So I'll just say 27 squared minus 9x squared with respect to x. Okay. Well, that 9x, we can replace that with 27 times sine of theta. So the integral of the square root of 27 squared minus 9x, which is 27 times sine of theta squared, dx, well, that dx, we can replace that too. So it's times 3 times cosine of theta with respect to theta. And I don't really need the parentheses. I'll put the little multiplication dot. Okay. So here we'll have 27 times sine of theta squared. We'll have 27 squared times sine squared. So that 3, we're just going to go ahead and factor that right onto the front just to get it out of the way. So we have 3 times the integral of the square root of 27 squared, or if you want to put 729, you can. I just choose 27 squared minus 27 squared times sine squared of theta times cosine of theta with respect to theta. Okay. Well, both of these happen to have a 27 squared as a factor. So we can factor that out of both of those. So 3 times the integral of the square root of 27 squared times, that leaves us with 1 minus sine squared of theta times cosine of theta with respect to theta. Well, that 1 minus sine squared should look familiar. And it does because we know that sine squared plus cosine squared is equal to 1. So if we subtract sine squared from both sides, that gives us cosine squared is equal to 1 minus sine squared. Okay, so if we square root both sides, we know that cosine, well, the square root of cosine squared is just cosine, is equal to the square root of 1 minus sine squared of theta. Okay, which means we have to get that square root of 1 minus sine squared of theta by itself. And since we're being multiplied by that square root of 27 squared, well, that 27 squared, we can separate those two. Because we know that the square root of a times b is equal to the square root of a times the square root of b. So we can split these two up. And that leaves us with 3 times the integral of the square root of 27 squared times the square root of 1 minus sine squared theta times cosine of theta with respect to theta. And let me finish this on the next page. All right, anyone still writing? All right, let me write down where we left off. Left off at 3 times the integral square root of 27 squared times the square root of 1 minus sine squared theta times cosine of theta with respect to theta. And we also left off knowing that cosine of theta is equal to the square root of 1 minus sine squared of theta. Okay, so we know that the square and the square root will cancel each other out. So that just leaves 3 times 27, that 27 you can factor out. So 3 times 27 times the integral, and that square root of 1 minus sine squared of theta, we can replace that with cosine. The integral of cosine of theta times that cosine of theta that's already there with respect to theta. Okay, so 3 times 27, we can just replace that with 81 times the integral. Cosine times cosine is cosine squared of theta with respect to theta. So that big old mess did kind of become something somewhat manageable. Okay. And we know that whenever we have a cosine squared, we can just replace that cosine squared with 1/2 plus 1/2 cosine of 2 theta using a trig identity. Okay, so that's 81 times the interval of 1/2 plus 1/2 cosine of 2 theta with respect to theta. Okay, so now we just have to find the integral of each term. That's 81 times the integral of 1/2 with respect to theta is 1/2 theta. Plus 1/2 times the integral of cosine of 2 theta is 1/2 sine of 2 theta. Plus c. And we'll solve that over here on the side. Well, actually, we don't even have to solve it. We just have to remember, again, that if we're using trig functions, we have to have actually that one's just u substitution. So we don't have to really solve that one. Okay, but that sine of 2 theta, we can rewrite that as 2 times sine of theta cosine of theta. Again, using the trig identities. And I'm trying not to have this side too filled up. Okay, so all those trig identities, you definitely want to have that sheet with you if you kind of forgot those. And again, completely understandable not to remember all of those. It's a lot of them. So having those handy really does help. Okay, so instead of 1/2 sine of 2 theta, straighten that up, we can replace that sine of 2 theta 81 times, and we can distribute the 81 if you like, but I usually wait till the end because different numbers keep popping up. So 1/2 times theta, and if we multiply these two, 1/2 times 1/2, we get 1/4. Instead of sine of 2 theta, we're going to replace that with 2 times sine of theta cosine of theta. Plus c. Okay, so if we go ahead and multiply these two, 2 times 1/4, that's just 1/2. And that's why I usually wait before distributing, because these numbers will constantly change. So you have 1/2 theta plus 1/2 sine of theta cosine of theta plus c. Okay, so just kind of make it easier, we can factor out 1/2. I mean, not much you can do to make this easier, but we do what we can. That's 81 divided by 2. That's theta plus sine of theta, cosine of theta. Plus c. Okay. So again, that's correct, but it's giving us a solution in terms of theta. We don't want a solution in terms of theta. We want a solution in terms of our original independent variable x. So what we're going to do is we're going to replace all of those and make that a little bit wider. Here we go. Excuse me. Okay, so if you remember, we know that u is equal to, I believe, 9x. Yep, u is equal to 9x. And a is equal to 27. Okay, so we want to solve for theta. So we know that sine of theta is equal to u over a, which is 9x over 27, which simplifies to x over 3. So if we want to solve for theta, we have to apply, let me put sine of theta equals x over 3. Apply sine inverse to both sides, because sine and sine inverse are inverse functions. The only thing left will be the argument. Okay, so we have sine inverse of sine of theta is equal to sine inverse of x over 3. So again, the sine inverse and sine cancel each other out. That means we know that theta is equal to sine inverse of x over 3. Okay, which works fine for the thetas here, but now we have to get rid of the cosines and sines, but we'll do that afterwards. Okay, so now we have our theta, that's 81 divided by 2, times theta, which is sine inverse of x over 3. Plus sine of theta, so that's just sine of sine inverse of x over 3. Yep, this is going to be a long one, so let me erase that line. Times cosine of theta, which is cosine of cosine inverse, sine inverse of x over 3. But we don't want cosine of sine inverse of x over 3. We want cosine of a cosine inverse, because that will cancel out the cosines. Okay, so if you get the cosine of a sine inverse, that really doesn't help very much. So we have to find a cosine inverse. So we're going to remember that our, make that a little bit wider. Hopefully we have enough room. And there we go, that ought to be enough. We know that cosine of theta is equal to the square root of a squared minus u squared divided by a. That's just the adjacent over hypotenuse if we use the triangle. Okay. So if we apply cosine inverse to both sides, just like we did up here, the cosine inverse and cosine would cancel out. So we know that theta would equal the square root of a squared, which is 27 squared, minus u squared, that's minus 9x squared, divided by a, which is 27. Oh, forgot my cosine inverse. So busy worried about having enough room, I forgot to write the cosine inverse. Hopefully I'll still have enough room. I'll just write cosine inverse kind of small. So cosine inverse of the square root of 27 squared minus 9x squared squared divided by 27. Okay, so this one, we can actually simplify it. So instead of 27 squared, we can make it 9 times 3 squared, which means we'll be able to factor a 9 squared out of both of those. So theta equals cosine inverse of the square root of 9 squared. So that 9 times 3 squared still leaves us with 3 squared minus x squared divided by 27. Okay. And that square root of 9 squared just leaves us with 9. So cosine inverse of 9 times the square root. Actually, that factors out, so I don't need the square root over that one. That's just 9 times the square root of 3 squared minus x squared is just 9 minus x squared over 27. Okay, so we know our theta now in terms of cosine inverse, so that helps a lot. Okay, so now we can replace that theta with cosine inverse, and it will get rid of the cosine. Let me see if I can make that a little bit smaller to try and fit it all in there. Times cosine inverse of 9 times the square root of 9 minus x squared divided by 27. And I'll put a plus c there. After all of that, last thing I was really worried about is room for the plus c, but I'll throw it in there. Okay, so here the cosine and the cosine inverse cancel out. Okay, so that leaves us with 81 divided by 2 times the sine inverse of x over 3. This sine and this sine inverse cancel each other out. So that just leaves plus x over 3 times this cosine and this cosine inverse cancels out. Say 9 times the square root of 9 minus x squared divided by 27 And we have room for our plus c finally. Okay, and the only thing left to do is just simplify. So this 9, 3 goes into 9 3 times, 3 goes into 27. Actually, we can just go ahead and take it into 9. I don't know why I was doing 3. 9 goes into 9 once, 9 goes into 27 3 times. So if we go ahead and multiply those two, after all of that, we are finally left with our answer of 81 divided by 2 times sine inverse of x divided by 3 plus x times the square root of 9 minus x squared divided by 9 plus c. And again, I don't think Newton even wants you to put the plus c in there. At least I don't think they were. Most time they'll say don't worry about adding the plus c. All right. Now I know there's got to be some questions about this one. This one was a mess. No questions? Hopefully because it kind of made sense. Okay. Now I don't want you to think that this is one of those problems where, oh, it just flows right through. There's a lot of trial and error. Let me try this. Okay, that didn't work. Let me try that. Okay, so you're just seeing the end result of trying this and trying that. This didn't work, so let me try this. That's all this is. So I don't want you to think, oh, it just kind of flowed. No, it didn't. Okay, how long you've been doing it, you're still going to have try this. Oh, that didn't work. Let me try that. So it didn't all just flow. This is just the end result of trying that. So do not be afraid of trying something and saying, oh, that didn't work. Let me try something else. No matter how long you're doing this, you're going to encounter problems where you have to do that. So if you try it and it doesn't work, at least try not to get frustrated. I can't say don't get frustrated because it's going to happen. So just remember it's part of the process. All right, leave that up for a little bit. And I'll do this one next. Do one more example. This one really isn't as long, so. Well, this one was one of the longer ones. Even though at the beginning it doesn't look like it would be a long one, but. All right, anyone still writing? Okay. Okay, so let's say, for example, we wanted to evaluate the integral of dx divided by the square root of 4x squared plus 1. Okay, so again, it's not in the forms that we had at the very beginning. Okay. So it's over, well, you could move the dx and you can say 1 over the square root of u squared plus a squared. Here we have a squared minus u squared under the square root. We have an a squared plus u squared, but there's no square root, so it doesn't fit any of those original ones. So always check the original 3 first. Those, if it fits in any of those, then it's a lot easier. You're just kind of plugging it in. But if it doesn't, then we have to check the others. So if you notice on this one, it contains the square root of u squared plus a squared. Doesn't matter which order. Since addition is commutative, you can switch them around. This is u squared plus a squared. Okay, so we know with the u squared plus a squared, we're going to use tangent, well, square root of a squared plus u squared. We're going to use tangent. So we have to find our tangent of theta, solve for that u, and our secant of theta. So that gives us the square root. That 4x squared, we can rewrite that as 2x, and that quantity squared. Plus 1, we can rewrite 1 as 1 squared. So we know that u is equal to 2x, and a is equal to 1. Let me put that 1 in parentheses up here just for my own sanity. So write it as 1 squared. Okay, so we know that tangent of theta is equal to, if we look back, it's 2x over 1, which is u over a. Or you can just say 2x. But I'll leave it as 2x over 1, only because if you don't remember which triangle or how the triangle is, just remember that this is your opposite and this is your adjacent. That's why I left it as a fraction. Okay, so we can go ahead and create our right triangle. Where this is our angle theta. And opposite over adjacent, the opposite is over here, the adjacent is right here. And if you use the Pythagorean theorem, it will solve for the other side, which is 2x, that quantity squared plus 1, or 4x squared plus 1. Okay, so we know that since tangent of theta is equal to 2x divided by 1, which is just 2x, divide both sides by 2, we see that x is equal to tangent of theta divided by 2, or you could just say x is equal to 1/2 tangent of theta. Okay, so we have our x. Okay, now we need our dx. So our derivative of x is equal to the derivative of tangent, which is secant squared. So that's 1/2 secant squared with respect to theta. Okay, and if you remember, we also need our secant. That's going to come in handy. Okay, so we know that secant of theta is equal to the hypotenuse over the adjacent, since it's the reciprocal cosine. So that's the square root of 4x squared plus 1 over 1. Which means that secant of theta is just the square root of 4x squared plus 1. Okay, now this one actually works out fairly nicely because we have our dx divided by the square root of 4x squared plus 1. We know that our dx is equal to 1/2 times secant squared with respect to theta. So we're going to replace that with 1/2 secant squared of theta with respect to theta. Oops, forgot my theta in here. Secant squared of theta d theta. There we go. Divided by the square root of 4x squared plus 1. Oh, luckily for us, that's just secant of theta. So that 1/2, we can go ahead and just factor that right out to the front. And secant squared divided by secant is just like saying x squared divided by x. So secant squared divided by secant is just secant with respect to theta. Okay, well, we know that the integral of secant theta is the natural log of secant theta plus tangent theta. Actually, didn't even need this parenthesis here because I'm not going to distribute it to my plus c. So we can just keep that as 1/2. And then just put the plus c. Okay. So now we can use our triangle to convert secant of theta. Well, we don't have to do it for secant of theta because we already have it. And we convert our tangent of theta, but we already did it since we have 2x. Okay, so that gives us 1/2 times the natural log of secant theta, which we can replace with the square root of 4x squared plus 1. Plus tangent of theta that we can replace. Trying not to draw too many arrows, but I don't want anyone to say where to get that tangent of theta from, which is 2x plus c. Okay. So sometimes you get lucky and you get one that takes less than 2 pages to complete. All right, any questions on that one? All right, I'll leave that up for a little bit. All right, anyone still writing? Okay. So now we're going to go ahead and start on section 7.3. Which covers partial fractions. Again, very, very, very useful. Okay. So with this one, let's say, what if we wanted to integrate, say, the integral of 1 divided by x squared minus 5x plus 6 with respect to x. Okay. I think its u substitution wouldn't work. Any method we've tried so far wouldn't work. Okay. But we can rewrite this. Okay, so what if you could figure out that 1 divided by x squared minus 5x plus 6 is equal to 1 divided by x minus 3 minus 1 divided by x minus 2. And you can double check. All you have to do is multiply the first term by x minus 2 over x minus 2, and the second term by x minus 3 over x minus 3, and then just simplify. Okay, so that means that we could have the integral of 1 divided by x squared minus 5x plus 6 with respect to x. And we could just rewrite it as the integral of 1 divided by x minus 3 minus 1 divided by x minus 2 with respect to x. Just replace the function with an equivalent function. So if we distribute the integral, that's the integral of 1 divided by x minus 3 with respect to x minus the integral of 1 divided by x minus 2 with respect to x. And that just gives us the natural log of the absolute value of x minus 3 minus the natural log of x minus 2 plus c. Okay. So converting these, well, this one to this one, is partial fractions. And there are different methods depending on the type of partial fraction that you run across. Excuse me. All right, anyone still writing? All right. Okay, so this is just one method. And this one's pretty popular if you're dividing improper fractions. Okay, so this one might kind of take you back to your intermediate algebra days and probably college algebra too. I think it was covered in that too. So what if we wanted to evaluate the integral of negative 3x squared plus 12x minus 12 divided by x minus 1 with respect to x? Okay, so with this one, you want to take your function and just divide it. So it's negative 3x squared plus 12x minus 12 divided by x minus 1. Okay. Now, if you wanted to, you could use synthetic division, which is a lot easier. But with synthetic division, it's only useful, or you can only use it in certain forms. So this one would take up probably a nice chunk of the page, but with synthetic division, kind of give it a little reminder. Again, it's a lot faster, and I recommend using it whenever you have your, not divisor, divisor. That's your radicand, that's your divisor. Had to remember which parts, which of a square, of a fraction. Okay, so that gives us, let's say if you have some value that we will call k. Okay. And you list all of your coefficients in kind of an inverted division sign. Okay. So since this is a square root function, I'm going to go ahead, not square root, a quadratic function. I had to remember the right name. I'm going to go ahead and write a quadratic example. So you have ax squared plus bx plus c. Actually, let me make that a little longer. Let's make it to the third power squared x plus d divided by x minus k. And of course, it can go a lot longer than that. This is kind of just a quick review of synthetic division. So the first thing you do is you write down all of your coefficients in that flipped division sign. So you write your A, your B, your C, and your D. Okay. So your first coefficient, you just bring that down. And then you multiply k times whatever that first coefficient is, and you add it to your next term. So if you add them together, you get some number. We'll call that number f. So then you multiply k times that number and add it to the next term. Bless you. So let's say we add those numbers together and we get some number that we will call g. And you multiply k times that number and add it all the way down till you get to your last term. Once you reach your last term, you add those together. Let's say that's some value r, that's your remainder. So it really is a whole lot faster than trying to do it the long way, as long as your denominator's coefficient is 1. So I'm hoping that looks familiar. So if we get our negative 3x squared plus 12x minus 12 divided by x minus 1, we use synthetic division. You see if we match these up, your k is equal to 1. So that means on the outside, we go ahead and put that 1. And we get our little flipped division bracket. And we write all of our coefficients. So we have negative 3, 12, and negative 12. Okay. Now the first coefficient, you just bring that right on down. And then you multiply 1 times negative 3, which in this case is negative 3. And you add those together and you get 9. Then you multiply 1 times 9, which is 9. And you add those together and you get negative 3. Okay. Now converting this to your answers, not too bad. So up here we have negative 3x squared. I'm just kind of writing these up here. You don't have to. Plus 12x minus 12. That's just your constant. So we'll just say that the constant c. All you have to do is subtract 1 from each exponent when you bring it down. So this x squared means this would just be x to the first power. This x to the first power is just x to the power of 1 minus 1, which is 0. So that's just a constant. And this last one, remember, that's always going to be your remainder. Let me move that up a little bit. So once we do that, we know that we can just rewrite our integral of negative 3x squared plus 12x minus 12 divided by x minus 1 with respect to x. We can rewrite that as the integral of negative 3x plus 9 plus the remainder, you can put minus if you want to, but I'll say plus the remainder of negative 3 out of x minus 1 with respect to x. And you can verify that these are equivalent functions. All you have to do is multiply the first two terms by x minus 1 over x minus 1. And once you combine like terms and everything, you will end up with the very same function. So now all we have to do is just integrate each individual term. Okay, so the integral of negative 3 times x is x squared over 2. So it's negative 3 times x squared over 2, which is negative 3 over 2 x squared. Plus the integral of 9 is just 9x. Plus the integral, might as well say negative 3. Factor that out, we have 1 over x minus 1. The integral of 1 over x minus 1 is the natural log of x minus 1. So it's minus 3 times the natural log of x minus 1 plus c. So where this one looks like a big old headache, you can convert it to something a little bit less time consuming. All right, any questions on that one? Excuse me. All right, anyone still writing? All right. Okay, so let's say, for example, if you wanted to integrate negative 9x squared plus 48x minus 22 divided by x minus 5 with respect to x. Okay, so we can see this is an improper fraction. Numerator is much larger than the denominator. So since we have an improper fraction, we can just go ahead and divide it and simplify that entire function. Okay, so it's x minus k. So we know that in this case, our k is equal to 5. Okay, now if you might run across one like this, let's say your denominator is x plus 5. Then you're just going to rewrite it as x minus negative 5. And in this case, your k would be negative 5. So if x plus 5. Okay, so that's just a side note. That's not really involved in solving this one. Okay, so we're going to go ahead and use synthetic division. And again, you'll see how quick it is without all the extra writing. We're going to put our k on the outside. And then we're going to write down the coefficients. Negative 9, 48, negative 22. Okay, we bring down the first one. And we're just going to multiply that 5, that k value, to each and every value that appears below that inverted division bracket. Okay, so 5 times negative 9 is negative 45. I'm going to add those two together. So 48 plus negative 45 gives us positive 3. Now we're going to multiply 5 times 3, which gives us 15. We add those two together. Negative 2 plus 15 is negative 7. Okay, so again, it's really quick to use synthetic division. So now all we have to do is get our new function. So remember, this was negative 9x squared plus 48x minus 22, which was just our constant. Every one of those exponents just goes down 1. So instead of x squared, that's just x. Instead of x to the first power, that becomes x to the power of 0, or just the new constant. And that last one is always going to be your remainder. So that means we can take the integral of negative 9x squared plus 48x minus 22 divided by x minus 5 with respect to x. And we can rewrite it to the much more appealing negative 9x plus 3 minus 7 over x minus 5 with respect to x. And then we can integrate this one. So negative 9 times the integral of x. So the integral of x is x squared over 2. That's negative 9 over 2. Let me make that a little further left, just to make sure we have enough room. So negative 9 over 2 x squared plus the integral of 3 is 3x. And if we factor out that minus 7, that gives us 1 over x minus 5, and the integral of 1 over x minus 5 is just the natural log of x minus 5, and plus c. So once you get kind of re-familiar with dividing polynomials using synthetic division, problems like this can go by really quickly. All right, any questions on that one? All right, anyone still writing? All right. Now we're going to look at if you have non-repeating or also known as distinct linear factors in the denominator. Okay, so let's say if you happen to have a function f of x, and that function is just a quotient of two functions. So your numerator will say that function is p of x, and your denominator will say that function is q of x. Where we know that that q of x can be factored. Let's say q of x is equal to a sub 1 times x plus b number 1 times a sub 2 times x plus b number 2. And it keeps on going until you eventually reach a finite number of factors. Okay, so assuming that all of those factors are different, none of those are repeating. All the coefficients are different. Well, they could be the same coefficient, but we know that they're not identical. And we know that we can take our p of x divided by q of x and make that equal some value a sub 1 divided by your first factor. Plus some value we'll call a number 2 and divide it by your second factor. Plus, and it keeps on going all the way until you finally reach that finite number a sub n divided by your finite or your last factor, a sub n times x plus b sub n. All right, so let's say, for example, we want to evaluate the integral from 5 to 6 of 2x plus 7 divided by x plus 2 times x minus 1 with respect to x. So we can see in the denominator, x plus 2 times x minus 1, they're non-repeating factors. So they're distinct. Okay, so x plus 2 and x minus 1 are non-repeating or you can just say distinct factors. Just kind of identify what they are. Okay. So because they are non-repeating distinct factors, then we know for a fact that we can rewrite 2x plus 7 over x plus 2 times x minus 1. We can rewrite that as some number divided by x plus 2 plus, and you can use a1, a number 2, a number 3. I just use a, b, c, d, e. Just a lot easier. So we know we can factor it out to two terms. We have some number divided by x plus 2 plus some number divided by x minus 1. Now, to find out what those numbers are, all we have to do, and I normally don't write this first one down, I just put equals, but I'll write it down anyway. X plus 2, x minus 1. This a divided by x plus 2, just going to multiply the numerator and denominator by the opposing denominator. So a divided by x plus 2, we're going to multiply that by x minus 1 over x minus 1. Plus that b divided by x minus 1, we're going to multiply that by x plus 2 over x plus 2. So the whole point is to have all three with the same denominator. So if you multiply each one of those by their common denominator, all of those denominators would cancel out. So that leaves us with 2x plus 7 is equal to a times x minus 1 plus b times x plus 2. So now we want to get rid of those parentheses, so we're going to go ahead and distribute a, and we're going to go ahead and distribute that b. So we know that 2x plus 7 is equal to a times x minus a times 1, so that's just minus a, plus b times x plus b times 2, or you can just say 2b. 2b or not 2b. So now we want to combine all of our like terms. So we have two terms of x, and we have our two constant terms. So we want to just put those together. So we know that 2x plus 7 is going to equal, you have ax plus bx. If you factor out that x, that's just a plus b times x. Plus, we get our two constant terms, we can just make it negative a plus 2b. Nothing really fancy we have to do with that one. Okay, so with this, we want to solve for a and b. Now, there are a couple of methods you can use, and honestly, I'll show you two, and you can pick whichever one you feel is best for you. I have no preference either way, but it's best to know both because sometimes one won't work and the other one will. So you want to be familiar with both. So this is method number one. Okay, so we can see here that for this x term to be equal with this x term, that means a plus b would have to equal 2. So I'll just rewrite it. 2x plus 7 equals a plus b times x plus negative a plus 2b. Just rewriting that so I can mark up this one instead of the original. So this a plus b would have to equal 2 in order for that to be equal. So we know a plus b would have to equal 2. And these constants, when you add them together, they have to equal 7. So we know that negative a plus 2b has to equal 7. So it doesn't matter which one you start with, but we have to isolate one of those unknown variables. So let's say if we subtract b from both sides, we can say that a is equal to 2 minus b. And what we're going to do is we want to get that and just plug it right into that one. So that negative a plus 2b, negative a plus 2b equals 7. We're going to replace that a with 2 minus b. So that's negative 2 minus b plus 2b is equal to 7. So again, we want to get rid of those pesky parentheses. So we distribute that negative 1. So we have negative 2, negative 1 times negative b is positive b, plus 2b equals 7. And I'll finish this up on this page. So we combine your like terms. We have negative 2 plus 3b is equal to 7. So we can go ahead and add 2 to both sides, which means that 3b is going to equal 9. Divide both sides by 3. We know that b is equal to 3. And this one you can plug into either equation. Okay, so we can plug it into a plus b equals 2, negative a plus 2b equals 7, a equals 2 minus b. You'll get the same answer either way. So if we plug it into a equals 2 minus b, that means that a is equal to 2 minus 3. That means that a is equal to negative 1. So that's method 1. And I'll put a little square showing that that's the end of it. Like I said, which method, completely up to you. But it is, I would say necessary, but it's very, very important to learn both because there are ways around it if you don't know it, but this makes it easier. All right, anyone still writing? Okay, now the second method is what we call strategic substitution. And you'll get the very same answer. So method number 2, strategic substitution. Okay, so we know we have 2x plus 7 is equal to a times x minus 1 plus b times x plus 2. Okay, so what we want to do is we want to pick a value of x that would make one of those variables disappear. So we know here we can pick x equals 1. That would get rid of a. We can pick x equals negative 2. That would get rid of b. Okay, so let's say if we let x equal 1. So you have 2x, 2 times negative 1. I mean, 2 times 1, I might say negative. 2 times 1 plus 7 is equal to a times 1 minus 1 plus b times 1 plus 2. Okay, so 1 minus 1 is 0, so it doesn't matter what A is, it's disappearing. Okay, so 2 times 1 is 2, so 7 plus 2 is 9. So we have 9 is equal to B times 1 plus 2, so 9 is equal to 3B. So if we divide both sides by 3, that B is equal to 3. So now we let x equal negative 2. So that would give us 2 times negative 2 plus 7 equals A times negative 2 minus 1 plus B times negative 2 plus 2. Okay. So negative 2 plus 2 is 0, so that B disappears. So 2 times negative 2 is negative 4. Negative 4 plus 7 is 3. So we have 3 is equal to A times negative 2 minus 1 is negative 3. So you can just say negative 3A or A times negative 3. Doesn't matter. So negative 3A. So if we divide both sides by negative 3, we get A is equal to negative 1. So you get the exact same answer with both methods. Again, I would practice with both, but because there are some times where strategic substitution won't work. Even though to me it's the fastest, so always try it first. But if it doesn't work, there are other methods that we'll learn after this. Okay, so since A is equal to negative 1 and B is equal to 3, that means we can rewrite our integral from 5 to 6 of 2x plus 7 divided by x plus 2 times x minus 1 with respect to x. We can rewrite that as the integral from 5 to 6 of A, which is negative 1, divided by x plus 2, plus B, which is 3, divided by x minus 1 with respect to x. So again, all we did was take this really complicated function and made it a little less intimidating. Okay, so I'm just going to move the equal sign over here because I know this is going to get a little longer. So if we factor out that negative 1, the integral of 1 over x plus 2 is just the natural log of x plus 2. Plus, we take the integral, well, take the 3 first and factor that out. Take the integral of 1 over x minus 1. That's just the natural log of the absolute value of x minus 1. And we don't need the plus c because it's a definite integral. So we know that's from x equals 5 to x equals 6. Okay, so now we can go ahead and apply the fundamental theorem. We plug in our upper bound. So move that over to make sure we have enough room. Okay, so we have negative natural log of 6 plus 2 plus 3 times the natural log of 6 plus 1 minus negative natural log of 5 plus 2 plus 3 times the natural log, clean that up a little bit, of 5 minus 1. Yes.
When solving the sixes, shouldn't it be 6 minus 1, 3 on?
Oh, yep, you are right. Yep, thank you. Okay. So from there, we just simplify it. That's negative natural log of 6 plus 2, which is 8. And since 8 is positive, we don't need the absolute value. I mean, it shouldn't mark it wrong if you did, but you don't really need it. Plus 3 times the natural log of 6 minus 1. So that's the natural log of 5. Again, 5 is positive, so we don't need that absolute value. And if we distribute this negative 1, we can go ahead and save a step. So negative times negative is positive, so that's plus the natural log of 5 plus 2, which is 7, minus the natural 3 times the natural log of 5 minus 1, which is 4. And again, we don't need the absolute value because we know that value is positive, or the argument is positive. Okay. Now, Newton might take this one as the answer or as the correct answer only because this can be simplified. So if it can be simplified, but they may take it. But if they don't, just kind of go through it and simplify it just to be on the safe side. May reject until simplified. Okay, so again, I would try it. If they don't take it, then I would just simplify it, especially if you are positive that you know it's the right answer. Okay, so here we're going to just rewrite this. Instead of 8, we're going to make that the negative natural log of 2 to the third power plus 3 times the natural log of 5 plus the natural log of 7 minus 3 times the natural log, and instead of 4, we're going to make that 2 squared. Okay. So if you remember the power rule of logarithms, you know, whenever your argument has an exponent, you just get that exponent and move it down to the front. So this is just negative 3 times the natural log of 2. Plus 3 times the natural log of 5. Plus the natural log of 7. Minus, we're going to get that exponent and bring it down to the front, but we already have that negative 3, so we have to multiply it. So we have negative 3 times that 2, which gives us 6 times the natural log of 2. Okay. But we can combine like terms because we have a natural log of 2 term here, and we have a natural log of 2 term here. So we can combine these two. So negative 3 natural log of 2 minus 6 natural log of 2 gives us -9, natural log of 2. And those two can't reduce those anymore, so that's plus 3 times the natural log of 5 plus the natural log of 7. And that's about as simplified as it's going to get if they want an exact answer. Now, if they wanted a decimal approximation, I would have stopped right up here and just plugged that into the calculator. But with the exact answers, they can be a little picky. So that's why I was saying I would try in that form. But if they may even mark, simplified or in lowest form, then you have to kind of take it all the way down. All right. Any questions on that one? All right. So we will stop there only because I know that I'm not going to get through the next example in only 15 minutes. So that one will definitely take us over. So we'll stop there. And we'll pick this up tomorrow. So if you have any questions, of course, you can hang back and ask away. If not, I will see you. Well, I will see you tomorrow. Having Monday off threw my week off. I'm thinking today is Tuesday. You too. All right. You too. You too. All right. You have a good one.
Thanks, you too.
Oh, let me see. Oh, someone has a question. Okay. So the final exam is on Monday, June 25th, the very last day. And let me check on that syllabus now, see why it's acting up. Let me see. I'm not sure why you can't access the syllabus. Surprisingly enough, it opened right up for me. I know. If you're using your phone, I know sometimes with me, if I don't update my Google Chrome, if I try to open something over your laptop, it could be a browser update. Like I said, I have no clue. I am not a tech person by any means, but I just know that with mine, usually updating or closing and reopening the browser sometimes helps. Let me go into Student View and see if that works. A lot of times it'll let me know. And let me see. So if it works in Student View, I know it should. Yeah, it opened right up. So, like I said, the way this technology has been acting up, I'm surprised it's working, but yeah, it worked. You might have to download it first, which you shouldn't, but that might be a way around it. But yeah, it should open right up. But if it doesn't, I would try. Oh yeah, you're download. Okay, that's perfect. I know, I'm surprised it didn't open up for you. But yep, the final exam on the very last day. That's Monday, June 25th. All right, you're welcome, Donovan. You have a good day too. Okay, that'll work. All right. So if you email me, like I normally check my emails and stuff before I leave for the day, so I might not see the email until tomorrow. But even then, if you have a question, feel free to, write it down and save it till tomorrow, or I can see your email, then I can reply to it after class tomorrow. Like I said, it kind of depends on when I see it. But yeah, I'll usually reply either, like I said, probably after class tomorrow. You're welcome. You have a good day.